Let's conclude section 6.2 by discussing the Z sub alpha notation. And so the definition is, for the standard normal distribution, a critical value is a z-score separating unlikely values from those that are likely to occur. And so notationally, this expression z sub alpha denotes the z-score, the subscript alpha, so z-score, z with subscript alpha, which denotes the z-score z-score with an area to its right to its right equal to alpha. So it's spelled A-L-P-H-A. That is the first letter of the Greek alphabet. So that is the Z sub alpha, the critical value notation. So when a decimal value is given as a subscript with a z-score, this notation indicates that the z-score creates an area to its right, to its right equal to the subscript, equal to the subscript. So to find z sub 0.05, we ask what z-score will cause the area to the right to equal 0.005. So what z-score will cause 0.05 or 0.05 probable area to its right. So there would be the area here, 0.05. And again, whether we look for the area, the z-score, in the tables or use technology, z sub 005 is equal to 1.645. Another way of saying it is to say that the probability that x is greater than or equal to 1.645 is equal to 0.05. Okay? Now, the next question asks, find z sub 0.22. In other words, we're looking for a z-score so that the area to its right is 0.20. So here is the area, 0.20, and we are looking for the z-score that's equal to that. Okay. So again, if we use technology or use tables, this turns out to be 0.842. And again, I would encourage you to do this, either again technology or use tables. In case you use the z-score table, you cannot really look up this directly, but you know the whole area is 1, so you subtract 0.24 from it, so you know that this area is 0.80. So you go to the table, look on the area 0.80, and you find the corresponding z-score of 0.842. So this is 0.842. That is the z-score here. Okay. Similarly, when we look for the z sub 01, so it's a very small area, obviously. This area is 0.01 or 0.01 or 1%. So that would be equal to 2.326. Again, whether you use technology or use the tables. 2.326. So that's the z-score. So the important thing is not to confuse the area of 0.01 with the corresponding z-score. The next exercise asks for finding the symmetric z-scores that separate the middle 70% of the probability distribution. So the question is, since we're talking about the symmetric part, we want to find the z-score so that the middle here is 70%. Well, if that is 70%, that means the tails together must be 30%, or another way of saying it is that the, of course, equal to 0.70. That is to say that each tail must have 0.15, area of 0.15, or probability of 0.15. So an easy way to look it up in the table is to look up the area for 0.15, find the corresponding z-score, and you will find it is minus 1.04. So that's a z-score corresponding to 0.15. And since it's symmetric, it's on the other side 1.04. The next question is quite similar. Find the z-scores that separate the middle 92% of the area under the normal curve from the 8% in the tails. So again, we want to find the two z-scores that are symmetric, of course. And this is not quite to scale, but I just want to make it easier to see for you what I'm doing here. So we're asking for the 92% in the middle. So in other words, we know that this is 0.92. That means in both tails together we have 0.08, or in each tail we have 0.04. 0.04. And when you look up the z-score for the area of 0.04, this little area here, you find the corresponding z-score is minus 1.75, and since it's symmetric, it'll be 1.75 on the other side. So those are the two z-scores that we're looking for. Let's look at the next example, degrees Celsius. Assume that the temperatures in degrees Celsius on thermometers are normally distributed with a mean of 0 degrees Celsius with a standard deviation of 1 degree Celsius. A thermometer is randomly selected and tested. Find the probability that the randomly selected thermometer reads greater than minus 0.58 degrees Celsius. So in other words, the x is a temperature in degrees. Temperature in degree Celsius. So x is normally distributed. We're told that from the problem statement, with a mean of 0 and a standard deviation of 1. And so now, remember, 0 is here, and minus 0.58. 0.58 is here. And so the question is, what is the probability to find that the randomly selected temperature reads is greater than minus 0.58? So in other words, we're looking for this probability here. Again, if we use technology, it's pretty simple. If you use a table, we want to know the probability of x being greater than minus 0.58. And when you look that up, that turns out to be 0.719. So notice what's happening in this example. Here now, the horizontal axis has meaning in the sense that the numbers mean something in terms of degrees Celsius. And if you were to use a table for this, you look for the area corresponding to a z-score of minus 0.58, and then subtract that area from 1 to get this area to the right. Okay. The next question asks this: for the normally distributed thermometer readings described in part A, draw the sketch and find the temperature reading corresponding to the 82nd percentile. In other words, remember that's a temperature reading that separates the bottom 82% from the top 18%. So that would be about here. So in other words, we know this area here is 82%, or 0.82. 82, and we know this area here is 0.18. And when we look up the z-score corresponding to 0.82, we find that that is equal to 0.915. That would be the temperature reading. In other words, the probability of x being less than or equal to, well, what question would that be? Well, that would be, 0.915 degrees Celsius. Missed them here. And so that's equal to 0.82. And remember, this is a probability. This is a probability. So therefore, we go into the tables, we look for 0.82 and find the corresponding z-score of 0.915. So that's the degrees X in temperature. Yeah, as before, we define X as temperature in degrees Celsius. Temperature. Degree Celsius.